Alright guys, so we are starting the probability distributions unit. This is in chapter 7 of your textbook. So first of all, we should remind ourselves of our basic probability concepts. So PA is our notation which represents the probability of event A. So there's no multiplication going on here, this is just notation for the probability of an event. This is the likelihood that event A will occur. Remember that probabilities are always between 0 and 1. If we have this notation where we have this not A, this is the probability that A will not occur. We remember that either A happens or it doesn't happen. So these two probabilities have to add to 1. And then we also remember that empirical probability is experimental, versus theoretical probability is our calculated what should happen. So theoretical probability, again, is calculated. We calculate it from all possible outcomes of what should happen. Okay, so we take the number of ways of the thing that we want to happen divided by the total number of ways of anything happening, any possibility. And that gives us our probability of A. So for example, if I'm rolling a single die, the number of ways of getting a 4 is 1. Only one of the faces of those dies has a 4 on it. But there are 6 different faces in total. So the probability of getting a 4 is 1 divided by 6, or approximately 17%. Experimental probability, or empirical probability, is based on direct observation. So I run an experiment and I see what happens. I take the number of times the event happened divided by the total number of trials. How many times did I run the experiment? So here's an example of empirical probability. Best Buy tracks the number of computers it sold each day for 30 days. So computers that are sold that day, this is the number of computers that were sold. This is how many days that number of computers sold. So there were no days, there was one day in which 0 computers were sold. There were 2 days in which 1 computer were sold. There was 10 days where they sold 2 computers. There were 12 days where they sold 3 computers, etc. Okay? We can calculate the probabilities of each of these things happening. So there's 30 days in total. If I add all these up, I get 30, or I can check up here. It told me 30 days. So if there was one day where we didn't sell any computers, the probability of selling no computers, the empirical probability, is 1 divided by 30, or approximately 3%. The number of days that I sold 1 computer was 2 days. So the probability of selling 1 computer is 2 divided by 30, or approximately 7%. Okay, this is a probability distribution. So when I show all the different possibilities, all the different probabilities, that is a probability distribution. So it's not really anything new. We have to calculate all of the probabilities now, not just one. Okay, so first of all, let's look at some definitions. Some outcomes. An outcome is something that can be counted or measured. Okay, the outcome of the experiment is something that can be counted or measured. We are also going to be working with something called a random variable. We represent the random variable with a capital X. All right, each value for this random variable we refer to as a lowercase x. So the capital X represents all possibilities of the variable. The lowercase x represents a single specific possibility for that variable. All right, and we do that for every outcome in the experiment. So for example, a dice game. Each face of the die corresponds to a single value or single outcome. Therefore, there are 6 different outcomes of a game using a single roll of a single die. We also need to remember the difference between discrete and continuous variables. So discrete variables are values that are separate from each other. So for example, a dice roll can be a 2 or 3, but it can't be 2.5. Shoe size can be 9, 9.5, or 10. Can't be 9.3. Number of people must be a whole number. I can't have half a person. All right. Discrete variables can also be limited. So a dice roll falls in the range of 1 to 6. I can't roll a 0 or a 7 on a standard die. Continuous variables can be any value within a range. So I can have a height of 161 centimeters, a height of 161.3 centimeters, a height of 161.375 centimeters. Okay, so I can be getting more and more specific. I can have all the values within that range. Other examples in height, I can have temperature, crime rate, speed, etc. Okay, anything that can have any value within that range would be continuous. Continuous variables also can have an infinite range. So compare the width of an electron versus the distance of Neptune from the sun. We've got very different values here. So a probability distribution, as I mentioned in our Best Buy computer sales example, is where we look at all the possible outcomes for an experiment, okay, or for a specific event. So we're looking at every single possible outcome, okay, and the probabilities of each of those outcomes. So typically we will see probability distribution done as a table where I show every outcome and the probability of each outcome. And sometimes you will see a probability distribution done as a graph as well, and that's usually as a bar graph. So here is the theoretical probability of rolling a single die. So they're theoretical probabilities. This is what should happen. So the probability of rolling a 1 is 1 in 6. Probability of rolling a 2 is 1 in 6. Okay, you can see that every different outcome has the same probability, 1 out of 6. Okay. This particular scenario is known as a discrete uniform distribution. Discrete because the variables are discrete. I can't roll a 1.5. Uniform because they are all identical probabilities. They are all exactly the same. Here is our computer sales that we looked at from Best Buy. There's the probabilities that we calculated, and here it is as a graph. Okay, so the number of computers sold, the probability of selling that many computers, and the number of times it happened. Okay, and again, this is empirical, meaning it's experimental from what actually happened. You can see that the number of computers sold, the sales, is my independent variable. It's on my x-axis, and the probabilities are on my vertical axis. Okay, the empirical probability. All right, the next one we're going to look at is the sum of 2 dice. So we need to remind ourselves, on the first dice I can roll a 1 to 6, on the second dice I can roll a 1 to 6, and here's the sum of those 2 dice. So I'm getting a sum of anywhere between 2 and 12. 7 is the most common, happening 6 times. So the theoretical probability for the sum of 2 dice, if I calculate these probabilities, 2 was only in my chart once, so the probability is 1 divided by 36, because there were 36 different numbers in that chart. A 3 happened twice, so the probability is 2 out of 36. You can see my 7 is 6 out of 36, and I work my way back down to 1 out of 36 for the 12. Okay, and as a graph, you can see that again. Again, the sum of 2 dice is along the bottom, so that's the sum that I would roll, and those are my theoretical probabilities along my vertical axis. We can also look at expected value, what we expect to happen, the average outcome that we would expect to get from a certain event. What we do is we take the outcome, so x1, the first value that happens, we multiply by the probability of that thing happening, so p at x1, all right, and then what we do is we add the next product. So the next outcome times its probability plus the next outcome times its probability. We write that like this: the sum of x times the probability of x. So we're doing the sum of the outcome times the probability of the outcome. Here's an example. So again, we're looking at our computer sales. You can see the probabilities here. So the number of computers sold 0 times the probability that that happens. Selling one computer times the probability of that happens. We've done this before. We multiply across the row and then we add up all of those results. Okay, so I get an expected value of 2.6. So what does that 2.6 actually mean? Okay, 2.6 is the expected value of computer sales. So it means that on any given day, I should expect to sell approximately 2.6 computers. Obviously, I can't sell exactly 2.6 computers. No one's going to walk out with part of a computer. So I'm selling anywhere between 2 and 3 computers, usually per day. Now, some experiments have certain values associated with the outcomes. So, for example, when rolling a single die, we can assign points for the different rolls. So, for example, maybe when we roll an even number, we'll add points, and if I roll an odd number, I'll subtract points. Okay? Or maybe we have 2 people rolling and one person gets points for rolling even, the other person gets points for rolling odds, something like that. Okay, so what happens here is our outcome column changes. So the outcome is no longer what was rolled. The outcome is now the points that we get for that roll. Okay, so let's look at an example here. So it's a 1-player game. We have a single die. So if you have an even number, you gain that many points. If you roll an odd number, we're going to lose that many points. So here's my chart here. This is the dice value just to keep track. So odd numbers, I'm going to lose points. So if I roll a 1, I lose 1 point. If I roll a 3, I lose 3 points. If I roll a 5, I lose 5 points. Okay? Even numbers I gain. So if I roll a 2, I gain 2 points. Roll a 4, I gain 4. I roll a 6, I gain 6. You can see gaining is addition, losing is negative. Okay? My probabilities are still 1 out of 6. So what I need to know is I need to know the expected value from this game. Remember, expected value, I'm going to multiply the x, the outcome that I'm concerned with, and in this case it's my points. So I multiply the number of points times the probability of getting those points to find out what the expected value of this experiment is. So in this case, when I add up all those products, I get 0.5. The expected number of points per roll is half a point. Now, quite often you're going to see questions like this. Is this a fair game? No. For a game to be fair, the expected outcome must be 0. Okay? It doesn't matter if you're playing with yourself or you're playing with another person. In data management, we consider it fair if the expected outcome is 0. Okay, so that is a key important thing to remember with these. Okay, so that's it. That's your whole first probability distributions lesson. Try some of the first questions of the homework tonight, and we can work on the rest of the homework in class tomorrow.